Let me introduce Dr. David Tonjes, and he is our first lecturer this fall. There will be 3 more lectures. You have seen the poster. There will be Monica Bugallo, there will be Thomas Woodson, and I will also lecture. And that will continue then in the spring. And then we recycle, we open up, so we do new research and we give new lectures. So it should be, and I'm very happy to see some of our graduate students here. That's what we also were missing in the past. I mean, the past, I do not overlook the whole past. I overlook the last 2 or 3 years. And I think this is good for a department like ours to come together, right? Not that we have only department meetings and then the students meet and so on, that we do something like this. So let me introduce David very, very quickly. I don't want to waste your time. He is a very comprehensively educated STEM scholar, I would say. David has started out, his professional life I'm only covering, started out as a math teacher for several years. And then he got a BA in liberal arts. And then he accumulated 3 master's degrees in computer science, in TSM, and in coastal oceanography. However that's correctly pronounced, I don't know. And he got a PhD in coastal oceanography. And as you all know him, as you know, he works on waste. And we shared that already, and most of you know. Over the years, David got grants to, I would say, nearly, look how he comes in. Over $1 million, and recently he won a new grant for $4.3 million from New York State to characterize New York State solid waste. And that's a 5-year program, and the 2 aspects to it. We will have with him now a new, after David Ferguson was the repeat member of the Millionaires Club with his grants. So we have now a follow-up on the tradition of this department to get $1 million grants and become a member of the Dean's Millionaires Club. And since David is working together with Elizabeth, she also becomes a millionaire in that context, which is not bad. It's very, very, very good. And the potential also is that this becomes a line item in the Albany state budget. So with other words, this runs now for 5 years, and if they are doing well, it may run for another 5 years, and so on. With other words, this department will have an enduring focus in solid waste characterization, and that is something that's appropriately for our department, because waste is a societal problem of industrialized societies, and that is something that is of enduring problematic, you could say. I mean, to have a center of research in this area is very good for this department and our society in the smaller context and in the wider context. And it is a world problem in a way, because we are still in the context of the Industrial Revolution, which started out in tiny spots in England not too long ago, when you overlook history. But it has then reached Europe and the United States and other industrializing countries, And now the whole world and the most populous countries in the world are industrializing. And that has a waste component of enormous consequences. So this is very valid a topic, and herewith I hand it over to Dave.
Good. All right, good. Thank you. Thank you, Dr. Schaefer. So, tough audience, because when you know everyone in your audience, it's unnerving. But tough audience.
Picture us naked.
Well, that's part of the, no, never mind. So I want to talk to you today about life cycle analysis, and I want to talk to you a little bit about solid waste planning and how they intersect. I've always had great hopes for life cycle analysis, and it's something of great promise, but I'm not sure that it's achieved its promise. But I'll talk to you about that as we go along. So, with the Department of Technology and Society, we've established this new research focus on 4 smarts, which would be engineering education, smart development, smart communities, and smart ethics. So this talk fits into the area of smart development and smart communities. It's a planning exercise, and so that's where I think it fits into our research in general. We need to make decisions about technologies in all areas of technologies. We have choices, and those choices require us to reach some decision about which we're going to implement or consider. The number one thing in this country, and I think around the world, in making a decision is cost. But often cost is not sufficient to describe your choice in altogether, and you need to bring in other things. So very commonly we do things called cost-benefit analyses, where we translate things that may not have a particular financial relationship into something that relates to money. But sometimes we can't do that with everything. And especially with environmental impacts, it's difficult to look at things in terms of dollars alone. On the other hand, if we want to get approvals for an activity, and we have a set of choices, it's easier for decision makers to reach a decision if they can look at numbers, if they can have some sort of a quantified basis for making a decision. If I can say this is a 4 and this is a 6, and higher numbers are better, then you can choose the 6 over the 4. If I say, well, this is a little bit better in terms of how the community views it, and this has a little bit less environmental impact, and then they say, well, but which is better? And that's a hard thing. But if I could put those in numbers, then people become happier. Solid waste is a really interesting field. It would jump down to the bottom. It's a multidisciplinary mess where you're often concerned with a lot of financial things, but you're also interested in technology reliability. It's heavily regulated. You have citizen involvement. There are often a variety of environmental impacts. You have multiple things that you're working on. You have multiple results from working with these things, and so it gets very complicated, and that complication can make you give you lots to work on for many years, as has been the case for me. But it can also make it difficult to say clearly what's a better decision to reach. So sometimes people look at these things and they say, well, EPA a long time ago said the best thing you can do with solid waste is not to have it in the first place. And so they call that waste reduction. They established a hierarchy of choices, I should say. And the first choice is waste reduction. Don't have waste in the first place. The second thing is to recycle it. The third is to burn the garbage and recover energy from it. And the last choice would be landfilling. And you can justify these choices, but they're just laid out as a hierarchy that should be followed. So that's one way you can make a choice. A second is to look at costs, and it can be a strict budgetary cost. New York State has also passed a law saying, for instance, you have to recycle things if it's cost effective to do so, and this is a law called General Municipal Law 120AA. And that law says when you're looking at the costs of recycling, you have to figure out, you have to compare them to what it would cost you to dispose of something, and what the costs might be if you weren't recycling it. And so it can be more than just a simple budget line. And then of course you can set goals. And a while ago in 1988, New York State set a goal and said we want to have 50% recycling. So if you had an activity that was going to contribute to meeting this goal, then it would be a good thing. In the latest solid waste management plan that New York State passed in 2008, they changed the goal from recycling to a disposal goal. So they said currently every New Yorker makes about 5.5 pounds of garbage a day. So within, the original plan said 10 years, it got stretched out to 25 years. They said we want to reduce that down to 0.5 pound per person per day of disposal, and because we can count disposal easily, and so that's an easy thing to quantify. But so you can make decisions on a variety of bases. And so, as I mentioned, New York State has formally adopted certain plans. The sort of fitting with the political, financial, engineering morass that garbage is. These are called swamps. So, but it's a solid waste management plan, and so in 1988 the plan was written so that you were supposed to comply with that hierarchy of first waste reduce, then recycle, and so on, to achieve 50% recycling. They enumerated lots of expected benefits that would come to the environment from doing so. But they didn't look at particular technologies and say, this technology is going to provide these benefits or these problems. The technology choice was supposed to be inherent in that notion of recycle first, then burn garbage, then landfill it. The 2008 plan was different. The state said, we want to achieve a 0.5 pound per person per day disposal goal, and we're not too worried about how you achieve that. We think there are particular ways of doing that are better than others, and you've got to try to reach that goal. Certain technologies will not help you to get there, but they said there's a whole bunch of ways for you to do that. What they did was they looked at some of those implementation pathways, and they used one of the life cycle analysis models I'm going to look at to quantify savings in energy and savings in the release of greenhouse gases, so that they could go to the governor and say, look, this is a worthwhile thing to do. Look at all the environmental benefits that are going to accrue from that. And then they also said, and by the way, we'll be landfilling less material, we'll be recycling more, and there'll be other benefits that the state can expect to reach. So, as I said, they did this through a life cycle analysis, and life cycle analyses are something that came out in the 1960s and 1970s. They had a much more complicated name then. Now they're called life cycle analyses. The notion being it's often a tracing from the beginning of a product to its end, if you look at it as a linear process. And so it's cradle to grave, start to finish. It's a modeling technique that is intended to produce quantitative values. Especially with the early ones, there was often a lot of not quantified values, but rather descriptive judgments. But especially in modern life cycle analyses, numerical values come out, and this technique was used quite early on with waste management and managing materials in general and products in general. So one example is diapers, and so this technique was really first being developed as I said, in the late 60s, early 70s, and at that time we were also making a transition from washing diapers to having disposable diapers, and this was and at the same time the environmental movement was developing, and so there became this sort of intersection of how much waste are we generating with when I throw diapers away all the time? What's the impact to the environment of doing this? Is the convenience factor associated with this justifiable in any way? We were changing from a traditional mothers staying at home and having time to wash diapers, and now both sexes were working and no one had time to do this sort of thing. The outside of a disposable diaper is plastic, and they're thought of as being plastic by most people. And plastics were starting to get an unsavory reputation even back then. And so we're putting these on our babies, and maybe that's not such a good thing. It was single use, and people we were in a huge transition from reusable objects to single use. We went from having refillable beer bottles and soda bottles to plastic bottles that we used once and then threw away. People were eating out at fast food restaurants, and there was no silverware, no plateware there. There was only things that were discarded, and people at home were switching from cloth napkins to paper napkins to plastic plates and disposable cutlery, and all these changes added up, and people said, aren't we making a lot more garbage when we do all of that? And is this a good thing? And are we doing the right thing for the world and for our children? And so there was uneasiness about these choices, although people were doing it. So this guy named Carl Lehrberger, who worked up in Albany, was hired by the New York State Diaper Service, a couple of large New York State diaper services, to determine if not to determine. He was essentially hired to find that disposable diapers had a large impact on the environment. And because his clients wanted to have good news, not necessarily just, well, they wanted good news, and so he did a report, and he did find that disposable diapers had larger impacts than reusable diapers. So Procter & Gamble didn't like hearing this, so they hired a couple of consultants, and each time the consultants did their report, they found that disposable diapers were better for the environment than cloth diapers. And then Lehrberger would go out and get more information, and he would say, no, you're wrong for these reasons, and then the disposable people would respond. And all along they were getting more data, and the scope of these studies were getting larger and larger and larger. They were bringing in more things, more considerations. And there are a lot of issues. So when you think about cloth diapers, this is all very nice and natural, but growing cotton takes an awful lot of water. a tremendous amount of pesticides, which is that the Aral Sea has pretty much disappeared in Central Asia because the Soviet Union diverted irrigation to feed cotton fields. There's oil extraction associated with the creation of plastics, and we all know that oil extraction causes tremendous environmental impact. So you need to consider that. When we extract oil from underground, we're losing that resource, we're depleting natural resources, but when we make the cotton or paper filler in the disposable diaper, we're also using up resources, and growing plants for the reusable diaper takes resources. Washing diapers takes a lot of water. When you put diapers in the landfill, at one time, one of the estimates were that diapers took up 30% of the space in a landfill, and then someone thought a little bit more about that and said no, and then someone actually went and dug up landfills and said no, it's more like 1.5%, but that's still a substantial amount of waste. People were concerned with what happens so Sheldon Reven, who was a professor in this department, used to tell a wonderful story about the love that, what future archaeologists were going to think about our society. And he said when they dig up a landfill, they're going to understand our tremendous love for our children, because they're going to find all of these feces carefully preserved and set aside for future generations to admire and consider. And because we landfill all of this waste, but the notion was, if you're putting feces in a landfill, are you making the leachate plume more toxic because of pathogens? And there's all sorts of considerations for energy. So obviously plastics, being a petroleum product, relate to energy use, and they're manufactured. But when you wash diapers, if you wash them in hot water, you have to heat that water, a lot of energy use. So these questions are not simple, and the fact that they came up with different answers is in some ways understandable. And the results did come out so every time Lehrberger did his results, wash at home was best and single use was worst, and every time Procter & Gamble did it, single use was best and wash at home was worst. But they were pretty much using the same data sets, they just argued over particulars, and so it's difficult to say. One of the big issues was, for instance, do people use two diapers often when they are diapering with a cloth diaper? And so Lehrberger said hardly ever, and Procter & Gamble said all the time. And so essentially what people have judged is, if water volume and water quality is a big issue, then disposable diapers are better for the environment. Otherwise, so long as you have adequate water treatment and energy isn't a big issue, then single use. I mean, then washing your own diapers is better. But water volume and quality is important for single use. Another example of an early life cycle analysis was to make a judgment about paper versus plastic with disposable goods. And as I said, so plastic replaced paper in so many different products. We had an explosion in fast food. You know, it's hard to, when we look around today, to understand that once upon a time fast food restaurants were not common. But they rapidly, in the 60s and 70s, became ubiquitous. And by 1990, 25% of the U.S. food dollar was being spent in fast food restaurants. And because McDonald's has between 40 and 50% of the fast food market, that meant that roughly 10% of all American dollars on food are spent in McDonald's. Isn't that a pleasant thought? Okay, so, and at the time, McDonald's came out with a revolutionary new product. It was called the McDLT. It was supposed to be a hamburger and a BLT mushed together, except they didn't want to mush it together, because if you mushed it together, then the lettuce and the tomato wouldn't be crisp. So they made this fancy double clamshell thing where the clamshells both closed over. They had two shells in one thing, and they folded over this way. And so you could keep the burger and its bun hot on one side, and the tomato and its lettuce and its bun cold on the other side. Now, McDonald's also has a rule that they don't want food to stand around for more than 10 minutes. Then they start discarding it. So this product, this elaborate polystyrene container, was made for a lifespan of about 3 to 4 minutes. And people looked at that and said, what a wonderful society we have. Look at how we use our resources. One of the reasons is that with polystyrene, in the 1980s, we had come to realize that the creation of polystyrene was affecting the ozone layer, and this was one of the great environmental crises of the 1980s because chlorofluorocarbons were used to expand polystyrene in those days. Okay, so Hawking back in 1991 got the first life cycle analysis published in Science, and he looked at what are the impacts associated with a plastic coffee cup compared with a coated paper coffee cup. And he gathered lots of information. He looked at it from manufacturing to disposal. A lot of his judgments today would be rejected as being insufficient because they were qualitative in nature, but he thought that plastic was a lot better for the world than paper. And this is because for the weight of a plastic cup is about 3 times less than that of a paper cup. So you get 3 times more use per unit mass when you use plastic, and so that carried the day in terms of his impacts. A relative flood of letters came into Science complaining about this, and they didn't like where he drew his boundaries. I'm sorry, I'm running long, but in the end, his views were sort of accepted. McDonald's therefore looked at this study, and they switched from polystyrene to paper. And the reason was they had entered into an agreement with the Environmental Defense Fund, and the people who support the Environmental Defense Fund know that paper is better than plastic, no matter what studies show. And so McDonald's, in order to appear more environmental, reached an agreement with the Environmental Defense Fund and stopped using polystyrene material. As these studies began to accumulate through the 1990s, there was a growing there was awareness that standardization had to occur. And this was linked with the growing use of risk analysis as a means of addressing especially regulatory issues. And risk analyses are very similar to life cycle analyses in a lot of ways. They're complicated models. It's not and data input is very important. So the Society for Environmental Toxicology and Chemistry pushed this beginning in about 1990, released a major publication in 1999, and then ISO, the great international standards organization, in 2006 released an updated set of rules for life cycle assessment. At about the same time, a nice peer-reviewed journal was instituted, and it publishes it publishes about 8 or 9 issues a year, and about 2,700 articles on life cycle analyses of various kinds. So there's been a community that's developed, and they've determined that if you want to do a life cycle analysis, you have to follow these basic rules, which is, establish your goal and your scope ahead of time. Determine what assumptions you're going to make. What functional unit, what is the mass that you're going to look at? Are you going to look at, for instance, 1 coffee cup? Are you going to look at a ton of solid waste? Are you going to look at all of the garbage that a community generates in a year? there are various ways that you can look at these problems, and they differ in how you do the work. You have to especially look at what boundaries you're going to have. Then you create an inventory of impacts, and this is the modeling process where you trace mass through a variety of processes and try to track pollution processes. Then you want to determine, is there an impact associated with these pollutions, and finally come up with some interpretation of your results and make some recommendations. So I'm going to start out. I'm going to walk you through a really basic life cycle analysis technique, and this is called WARM. It's the waste reduction model published by US EPA. They developed this in the late 1990s. We're up to version 15 now. I use version 14. It's simple because it only produces two results: greenhouse gas emissions, and it counts energy use. And it's designed to be done as a comparative model. So you have one situation and you have another situation. They're both in solid waste, and you want to see and you want to compare the output from them. So, and this, can you just hit the lights real briefly? So this is it's essentially just a complicated spreadsheet. And so you have rows of materials, and you put in the tons of generation for the materials and how they were managed, and the model then gives you an output in terms of energy, or on another page it'll give you the output in terms of greenhouse gases. And then you have a second scenario using the same amount of waste generation but managed in a different way. Yes, Todd.
Does this model or any of the similar ones have like sensitivity analyses built in?
It's not built in, but it's one of the ways that they look for model validation is through sensitivity analyses. Yeah. It's in the list of results interpretations. You should be doing sensitivity analyses.
Policymakers ask for that, or not so much?
Oh, heck no.
There is one.
No, they want an answer. So the data I used for this model was from an annual report put together by the town of Brookhaven. So we're going to look at the town of Brookhaven, where the university is located, and we're going to look at the information they supplied to New York State, which is not a full characterization of its solid waste, but it talks about what the town manages. Okay, now I ran into a problem from the start. So WARM wants to know how much of recyclables were disposed. So the town counts recyclables very carefully because they send them off to markets of one sort or another. But they don't know in the garbage that they generate how much of the garbage is recyclable or not. So I had to approach that in a secondary way, and so I used the US EPA has a model that estimates for the US as a whole what the composition of waste is. And so, for instance, they said there were nearly 2 million tons of aluminum cans made in the US in 2015, and that's out of 260 million tons overall. So that's 0.7% of the total waste stream. So I assumed that those EPA percentages held for Brookhaven, and so I could say aluminum cans in Brookhaven should be 0.7% of the total generation. They recycled this much. What's left over must have been disposed. And so that's how I backed into that. Unfortunately, Brookhaven claimed too much credit for yard waste recycling and tire recycling. So I had to take them out of the total waste stream, take them out of the EPA numbers, readjust everything, and redo my things. But essentially, that gave me my recycled and disposed tons, and that's what I could put into the model. And so for the Brookhaven model, because we didn't have all 40 some odd entries that the warm model has. We had fewer, about 15. This was the simplified spreadsheet that I had for each scenario for Brookhaven. So tons recycled, and then you could choose if you landfilled it, burned it, composted it, anaerobically digested the material, and it would give you the energy either saved or lost by doing this. Saved or used, I should say. So I had 3 disposal options for the town. I said, let's look if the town burns its garbage at its incinerator in Hempstead, which is what it does. I said, but let's assume that the town could also look at exporting its garbage to the nearest commonly used landfill, which is upstate in the Finger Lakes. It's a place called Seneca Meadows. It's against the law in New York State for us to bury garbage on Long Island, but I assumed that the law wasn't in factor, so I said, let's do a local landfilling and see if transportation makes a big difference. And if you're going to landfill garbage, then one of the big concerns with greenhouse gases and energy use is, are you capturing the gas and burning it to create energy, or are you letting all the methane get out into the atmosphere and causing a large greenhouse gas impact? So you have various options for gas system controls and recovery rates. For recycling, I assume that all the recycling happened locally. That's part of the way the model works, although it's not true. And I assume there was either no recycling, the current rates of recycling, or remember, I knew how much of recyclables were in the garbage, so I said, can we double the recycling rate? And if we can, let's assume we double it, and we pull more recyclables out of the garbage. Does that make a difference? All yard waste, I assumed, was composted locally which is true, at a local place called Long Island Compost. And Brookhaven is very entrepreneurial. They have a way of managing tires at the landfill that's very cheap, and so people like to bring tires to the landfill. So they get way too many tires into the system. But I said, what the heck, we'll take credit for all of that anyway, and we'll count them as being recycled. And so when I do this, I ended up with 20 different options, and you have recycling options crossed with disposal options, crossed with landfill gas options, and whether you're recovering electricity. And then you get an output from the model. And so to simplify things, I graphed these, and what we have here on is this is the savings. A positive number in this instance is savings of greenhouse gases, and so in other words, greenhouse gases less under this management program. Fewer greenhouse gases were emitted. And this axis is energy use. And so if it's a positive number, it means it also saved energy. And so this is for waste to energy, and lower recycling means fewer savings, and more recycling leads to more savings, but generally it's a good thing to do is to burn garbage, according to Warm. This is to export garbage, and we had options where if the landfill upstate does not collect their gas, then it has a negative energy and greenhouse gas impact in landfill, with the sole exception of one case where energy was not saved. All of the options, all of the recycling options, all of the landfill gas options are seen to be beneficial for the environment. I tested, and so this is the overall picture to put it in context. Waste to energy is generally a better choice. Recycling at home is a little bit more beneficial, but there's not that much difference between exporting garbage and landfilling at Brookhaven. So the transportation isn't a big factor with this model. I tested it using simplified data sets. Because it was hard to generate those numbers that I generated for those things. So I took, well, let's say I didn't make that effort. Let's just take the gross numbers here, and so then ran it through the same sorts of scenarios. And in red, these are the 3 scenarios in red, and they didn't make that big of a difference. So putting a lot of time and effort into getting very exact numbers may not make too much difference in your modeling output. So this model uses a lot of assumptions and parameters, but what's nice about WARM as an example of this kind of thing is it's very upfront about the assumptions it does make, and it's easy to look and see how they parameterize the model. When they're looking at greenhouse gases, the way they calculate it is they have some number for, they believe that they can quantify for all of the goods produced in the United States and in all 48 categories of stuff that they have, how much greenhouse gas is emitted when they make stuff all around the country. Okay, and so they say that your net greenhouse gases is this number minus any increase in carbon stock that may occur, minus the plus any avoided greenhouse gas emissions. So increased carbon stocks means what happens if you bury garbage and it never degrades, so that it's sequestered. Okay, so that'll impact greenhouse gases. The assumption in the model is everything is U.S. manufactured. When you look at the data sources, it's sort of interesting. This model version was 2016, but almost all citations were from 2010. A lot of them were a lot older than that, and so it's although they update it continually, they're updating the processes, not necessarily their parameters. They did have a very nice thing. They counted into the fact that because we recycle so much nowadays, when you have a new good, it's not necessarily made from virgin materials. It has some percentage of recycled goods in it, and so they factored that into their thinking. They also assumed, and this is for waste management nerds, that everything that was recycled got turned into the same thing again. So if you recycle newspapers, it becomes new newspapers. If you recycle soda bottles, it becomes new soda bottles, with the exceptions of corrugated cardboard, carpet, computers, tires, concrete shingles, drywall. But this isn't true. So, so for instance, major newspapers at most have 30% recycled content because recycled paper isn't strong enough. So, but we recycle 70% of our newspaper. Oops, anyway. It also assumed that there's no exporting of recyclables. All recycling occurs locally, which isn't true. And a major assumption, they've gotten better. They used to say that when you made compost and you put it in the soil, none of it ever degraded. But now they say only that 18% of things that go into a composting facility will never degrade. Again. I'm going to skip this slide for now. Yeah. Okay. And so a second model I looked at is this program called EaseWaste. EaseWaste is a European model, and it's different. It's a lot more complicated. Instead of having 2 outputs, they have a choice of about 10 or 12 outputs that the user can select to determine. It's complicated enough. Well, so WARM I was able to run by downloading the spreadsheet off of the internet and putting in the numbers. And if you want to run EaseWaste, you go to Denmark and you take a 1-week course. So a different level of complication. And even so, I sent Dr. Thyberg, when she was a student, to Denmark to learn this model. She now confesses she has no clue as to it's a really complicated thing that you have to stay on top of, and it's tough. So one of the things they do is they provide this really nice output that shows your scenario choice as a series of activities. And what this means is that for each one of these boxes, they're going to create the impact associated with that box. And that impact is going to get added on to the impact from the next box, and so on and so forth. So this is an aggregation of a whole variety of calculations. And so you can see this is three relatively simple scenarios to look at. What would happen if the town of Brookhaven wanted to do something with its food waste? What would the environmental impact be? And the choices would be to send everything off for waste incineration, or if you separated the food waste out, you could compost it in one of two ways, or you could put it into an anaerobic digester and then compost the residuals in one of two ways. So it's not a complicated situation, but this diagram gives you a flavor for the complication of the model. The model itself gets very, very complicated. And then you get outputs. And so in this particular output scenario, we looked at global warming. We looked at essentially, I always get this wrong. Ozone depletion, acidification of the terrestrial environment, eutrophication of the terrestrial environment, freshwater eutrophication, marine eutrophication, and the use of fossil fuels. And so this is the output that you get from one particular run of e-waste. Dr. Thyberg chose these categories as most representative for the things she was interested in. And so what they do is they have 48 specific materials categories, and they break the materials down into their constituent chemicals, because the way e-waste wants to determine impacts is to look at what happens to each chemical constituent as it moves through the process. So if you want to degrade food waste, you want to look at the organic contaminant of the food waste and the inorganic part of the food waste, and look at what's the degradation for the carbon and the fats, and for the fats, let's say, and the proteins, and so on and so forth. So you get very detailed process descriptions, often based on underlying chemistry and first principles. And so all of these things have to be specified and parameterized. And so the user can do all of this, or you can use the defaults that they give you, thank God. Because to have the knowledge and understanding to do this is difficult. You seemingly can change anything you want, but usually you don't have any reason to do so. So you use their default values. They have this wonderful description of what data is reliable. So remember, you have all of these thousands upon thousands of parameters, and you can rank them in terms of how reliable they are. And then you could, I guess, do a weighted sum of all the reliability and determine how reliable your model is. But anyway. And so, as I said, the output is was in 7 categories, and when you look at the output, you can get these really nice fancy graphs where your different choices are in, and I'm sorry this turned out in black and white, but you have fancy colors, and you can determine for global warming potential for each one of the 4 scenarios that we tested, what the impact from collection and transport, the burning of things, the recycling portion, the landfilling, the compost use. And you can do that for each one of your parameters and get all these very nice, complicated, and very pretty graphs. Okay? And then you say, then your decision maker says to you, okay, what does this mean? And that's a hard question. So because the processes are incongruent, how do you compare acidification of the terrestrial environment to the depletion of fossil fuels? Well, you could maybe you rank the results in some way. Maybe you treat them all as being essentially equivalent. Maybe you find some way of weighting them. I don't know. One way you can do is look at how each choice ranks in terms of relative to each other, and This is a favorite thing for Dr. Thyberg. She likes to do this sort of cross-scenario ranking. And so then you can get an average ranking and then say, okay, this must be best. Okay, so scenario 4 was identified as being having the least impact overall in terms of relative ranking. Or you can normalize it. And so, for instance, in Europe, they've quantified over 600 processes that produce pollutions, and so you can get of various kinds, and you can therefore look at the average burden to the average. You can look at the burden for the average person in the European Union, and then you can compare your result to that average burden, and so we can see the global warming impact here was about 2%. Of the average burden. And so theoretically, if all of these burdens were equivalent, now you can sum the burdens, and when you sum them, you see that, so the fourth choice was had the least mean burden too. But I don't know. A lot of assumptions there. One of my real concerns with life cycle analyses is you have these outputs. So terrestrial acidification. How do you measure terrestrial acidification?
Wait a million years.
Well, you could look at results, okay. But if you were asked to go out, if I said to you, I'll give you $25 if you'll give me a number for terrestrial acidification outside. Well, it's a compound term. It's the sum of various portions of acid rain, right? And that they've come together. There's no one measurement you can take that's going to give you terrestrial acidification. So if I say to you, this process is going to produce so much terrestrial acidification, there's nothing that you can go measure that's going to say, okay, yes, this process produces something like this amount of terrestrial acidification. So they don't actually measure the outputs. What they tend to do is they do two things. One is to do a sensitivity analysis, which Dr. Patinsky was asking for. So you take particular parameters that you think are key, you vary their value, and you see if it makes a big difference in the overall result. Or you can look and see, well, what did other people who did something similar find? And so that's ways that's interesting. One is a consistency well, they're both consistency measures. They're not really determination on whether you're getting anything accurate or not. So with these models, we have no clue whether they're accurate or not. Here's a consistency measure. So Franklin Associates, who are one of the people who did the diaper work against Lehrberger, they were hired by the state of Oregon, and they looked at a series of how many were these? I think it was 125 life cycle analyses on packaging, and what they said was, if they measured these commonly used life cycle analysis parameters, if they reported these results rather, what did they find? And the ones in green found that paper packaging was environmentally was better, and the ones in red found that plastic was better. And you can see there is some consistency for some things. So in human toxicity, paper has almost always been found to be better, although not always. But if you look at fossil energy use, there's pretty much equivalence between the different studies on which is worse or better. So these life cycle analyses don't agree with each other, even in the general trend of things. So the good thing about life cycle analyses, from my perspective, is there's no way to combine the outputs into single answers, even though that's what decision makers want. I like the complication of it. I like having to try to manage these things. I think it's appropriate. There is some general consensus across the models, and I'll talk about that in a second, but overall, models don't always agree. You can get to quantify things that are hard to quantify. And so you can say, is recycling, energy good for the energy budget? Okay, this model gives you an answer, and when you go to a decision maker, you have a result that has the strong appearance of being objective. It gives them a lot of authority. There's nothing like something that's quantified, has lots and lots of data that you can show people, and that is objective in nature. The bad thing is, of course, that there's no way to combine things into a single answer, because that's what decision makers want. So you really want to have a really good way of saying, this is better, this is worse. Different models give you different results. Even if they agree, even if they trend in the same direction, you rarely get the same exact output. We quantify things that should be sometimes less subjective, and they're objective, but underneath it all, you have all of these assumptions that you make, so you can bias your study in one way or the other. So maybe they don't have much authority. Okay, and we leave stuff out too, important stuff. So when I talk about all these studies of plastics, there's absolutely no mention of plastics in the ocean, and yet that's all people today want to talk about, because we don't know how to include them in a life cycle analysis yet. Economics are usually left out, and yet I began this talk by saying if you want to make a decision, the most important thing is going to be money. Way too many default values. It's very clear, when I was a young researcher and I was trying to do things that were beyond my competency, I would run around like crazy just to find a number I could use. And if I got the number, I was ever so pleased, and I used it, whether it was a good number or a bad number or a number that had no meaning. And so these models are chock full of that kind of thing. They found a number, put it in, we'll get better data later. The output graphs, how many of you thought those were good output graphs? Well, but there are lots of them, okay? And your model choice matters a lot as to what answer you get. Interesting things that almost all waste analyses say that if you're going to recycling is good, because you eliminate the energy use, a good portion of the energy use associated with making something from raw materials. So primary recycling is a good thing. As I showed you a little bit with the warm model, transportation, which is something that we're often very concerned about, doesn't seem to matter as much as we think it does. And so moving things around by truck isn't necessarily bad if you can find a better process. Recovering energy decreases greenhouse gases, so the two are often linked. And so if you can do something in waste management that generates energy, you're going to score very well in a life cycle analysis. So if you do waste energy incineration, if you burn your landfill gas, if you do anaerobic digestion and burn the gas. Composting and avoiding using plastics don't rank as highly as perhaps they should. A lot of environmentalists would tell you composting is one of the great things you can do, but it doesn't score very well on a lot of life cycle analyses. And plastics score really nicely compared to paper, so avoiding using plastic is not a good thing. And And that's because the benefits of doing so and the impacts associated with these things are not well quantified. So all models are wrong. George Box, this guy here, said that, and he added to that, but some are useful. And so in a life cycle analysis, you can quantify lots of things. The problem is, I don't know what those numbers mean. It's nice to have numbers, but what do they mean? It allows you to make justifications for your actions, but if it's not based on anything real, I don't know that those are real justifications. The modeling is really difficult to do with the really good models like ease waste, and you run into because they're so difficult to do. If you're able to do these models, well, you better think that the results have some meaning. If you're going to put all this time and effort and money into it, you can't say, well, that's nice. Now let's do some real work. You have to believe in it. And so you believe in these models, and someone says, well, you can't verify any of your results, and they say, well, that's not important. I ran a sensitivity analysis. That's good enough. And so you lose your skepticism where maybe you should have skepticism. In the bigger picture, life cycle analyses grew up at the same time, and they're very similar in a lot of ways to risk assessments. Risk assessments, again, tend to put outputs out that are difficult to verify. So if I say to you, exposure to perchloroethylene, dry cleaning fluid, is going to increase the risk of cancer by 1 in 100,000. How do I test if that is a true statement or not? I mean, about 300,000. About 30% of us will die from cancer. So 300,000 out of 1 million die. So if it's 300,001 or 299,999, what difference does that make? How do you test this sort of result? So risk assessments have the same kinds of basic problems with them, and the same issues associated with it. But the interesting thing about risk assessment is it drives our regulatory world, and so we don't want to question it. If the United States government is going to say to you, exposure to 5 micrograms per liter of lead is dangerous to your health based on risk assessments we've done, and the risk assessments are questionable, what water is safe to drink? How do I know this is okay? And we don't want to, so we don't ask those questions. We tend not to. They're really kept in the depths of academia. In the late 1990s, 3 sets of risk assessors were given the same data and asked to do a risk assessment for tris, which was a material put on children's clothing to keep it from burning. And one said the risk of cancer from exposure to tris was 1 in 7, and the other one said it was less than 1 in about 500 million. And the third was somewhere in the middle. But this is how we set our environmental laws. We don't messy. Okay, so let me get some acknowledgments. Dr. Thyberg did all the hard work that I showed. So the hard stuff out of ease waste, she did all of that. This group, New York State Association for Solid Waste Management, funded this. Town of Brookhaven supported Krista and provided the data. So I want to thank them too. And I'm done, and I'll answer questions. And I'm sorry I ran long. I'm not supposed to.
Wow, I have a better appreciation for the complexity. I feel like you're herding like a stadium of cats in doing this. So my question relates to maybe some of the sensitivity analysis. So like your original data reports, you've got the metals and
Right.
different sites. When they write those reports, when they create those, what I'm interested in is their incentive to be as accurate as possible, and so that you're using good data. Because ultimately, I imagine, so I'll finish my question in a second. I imagine, the funding agencies really interested in what you're doing, because then they want to see how transferable it is, that model, to other locations, and then be able to speak to it at a national and an international level. So going back to those reports, it was in the earlier slides. What is their incentive to be accurate? There might be some incentive to not be accurate. And the second thing, are they audited?
They're not audited. I wrote that report, so I vouch for its accuracy. Well, it's a report on the data that the town had, and the town is a public agency reporting to another public agency, and so there's the notion is you do it honestly. You can have problems with this sort of thing. So I said the town takes in a lot of tires, doesn't inquire too closely and care too closely whether all those tires are, quote, from the town of Brookhaven. So if this is supposed to be a report on the town of Brookhaven, well, it's in error because some of the tires didn't come from Brookhaven. And if that's a big issue, then there's issues.
I was thinking more of, like, say, the metals, for example. What if they're only reporting, like, 50% or 75%? Because otherwise, if they report all of that, then they have to pay more, or there's...
No, the incentives are just that most government agencies try to be open and transparent. A few of the three-letter agencies, maybe not so much so. But if the notion is if you're reporting to the taxpayers, you say what you did and how honestly. There certainly have been instances where where agencies will try to make themselves look very good. So one of the reasons why New York State no longer wants to talk about recycling rates is because it's easy to change those values. If you just find certain other, if you can make the numerator bigger without making the denominator too much bigger, then your recycling rate goes up. So there have been more than one instance of people inflating recycling rates, because that's something the public cares about and politicians care about. But generally, public information is good. With the sensitivity analyses, where it comes down to is getting all of these complicated reactions exactly right. Getting the big picture stuff. If you're going to compare your greenhouse gas impacts to the greenhouse gas, and you're going to add that into some sort of constant for what was associated when it was generated. You better get that number right, and it may make a big difference if something was manufactured in, I don't know, in Boston versus Detroit. They may be made entirely differently and have different impacts. And how do you address that kind of thing? I don't know. And it's sort of fun to think about the U.S. government as having counted greenhouse gas emissions accurately over manufacturing across the country. So,
David, you did a very good job of building these life cycle analysis up and then destroying it.
Yes.
So now I wonder, what's the third step? I mean, is there? I think I understand that these models are not reality, not building kind of imaging reality in a good. So if you can have so different outcomes with the same data sets, somehow there's a problem. And is there a way to resolve that problem? I mean, that you can, I understand you want to send many people here in this room to landfills and look what's there. So are you now approaching this problem that we get outcomes from these models that are somewhat instructive, but almost, I think, more, you presented it more in a way of potential critiques of methodologies that are used than in really representing the nature of the thing. And is this now going out there? Do you see a chance that you can actually come up with some accounting of what's happening that's closer to reality?
I don't know. Because I've always liked this sort of this thing. It's really cool to talk about, what's the overall impact of a process or of a thing. Is plastic better than paper in some fundamental way? And we need to understand these sorts of things. Yeah. But we can't fall in love with models that produce output, even though really, really smart people who are doing their best are producing these models, if we can't test them in some way. You can't put a lot of weight on it. Maybe you go back to making subjective judgments instead. With risk analysis, risk, for instance, and people have looked a lot harder at that in terms of decision making and so on. And risk analysts often get really, really, really frustrated when they produce a quantified assessment of risk and then people don't agree with it. They say, no, that's we can turn around and say to the average person, certainly less than, no matter what you think about Chernobyl, certainly less than 10,000 people have died from nuclear accidents in the course of nuclear power. And over that same period of time, upwards of 50 million people have died in automobile accidents. So, which would you rather live next to a nuclear power plant or drive your car? And everyone will say, "Oh, I want to drive my car." But they say, but look at the risk, because they're missing something. Their analysis doesn't capture something essential in our understanding of the situation. And again, these life cycle analyses, if you get an answer, you get a number, but you don't know what the number means, how can you present it to someone and then say, or you don't know if the number is meaningful. You know what it means, but you don't know if it's a true result or not.
Yeah, but my question.
You think it's the best we.
Do you see a way to know?
Well, so we try to do better. We try, people will refine these models and try to make the processes
but it's still
capture. They're still models.
Like,
yes.
It's like an algorithm, and there's a weighting factor, but each person puts a different weight to those factors.
It can be, and that can be it. Yes. Yeah. Ms. Byrne.
Does anybody, if you're looking only at recycling in Brookhaven,
yes,
specifically bottles, does anybody look at how many bottles of water, beer, things like this that come in recycled packaging are sold? And then these are consumable goods that probably are used within a year. So you could compare and assume that those things are coming out. And is there a way to correct your model or tighten it?
So that's the Environmental Protection Agency does that. They estimate all of the garbage in the country based upon what's made, what's imported, what's exported. Okay, and they pay this company a lot of money to do this, and then they figure out how long things last. So yes, bottles are used the same year, right? But a refrigerator.
Mine's 15 years old.
15. So a refrigerator lasts 20 years. So if you want to know how many refrigerators are being disposed of today, you look at sales from 20 years ago. Okay, and that sort of work, and you feel comfortable with that. You know, you think if I had really good data sets, I could do this accurately, and then you throw in the wild cards. You say, how do you get at yard waste?
Yeah, I don't throw mine out.
Well, but a lot of yard waste ends up in waste streams. So do you do a climate factor? Do you ask people? Do you count the leaves that fall in the woods? You know, how about food waste? Big issue now is the EPA keeps estimating there's more and more food waste in this country. How do they know? Remember, they do this input-output model.
Well, they know how many people live in the country, and so they know how.
And they know how much food is grown, and they know so one person tried that. They did, you know, the average caloric use by a person, and they knew how much food was grown, and they knew how much was exported, and they knew how much was turned into alcohol and all this stuff. And then they said, oh, okay, what's left over when we count weight gain for the average person must have been, well, it must have been either excreted or thrown out. And so you do an excretion number, and then you've got how much was thrown out. Well, that's accurate. I don't know. Yeah, it's the problem. You have these very, very data complicated problems, and even big data notions aren't necessarily going to help any with this stuff, because there's just uncertainty about the fundamental numbers, and that's at the bottom of a lot of these problems. Yes.
I was gonna say, so basically, like the life cycle analysis accounts, because like it's true what she said about the people not being audited, but at the same time I feel like that's already included with the different type of models that are made, and then you can compare like which ones are closer, like you showed us before, which makes sense. But I think it's hard to get accurate 100% data because, like you said, it's a really, really big sample of whatever you're trying to do, and it's like one little thing will mess up everything. Like one little thing will be like counted wrong or whatever, or counted whatever, more or less. But I think like my thing is like, isn't it important to like regardless show data, like have data that will help the environment regardless like of whatever. Like even if we do count that there's more food waste, we should still like require there to be a method to like.
You'd think, right? So the notion is that, you know, my parents brought me up not to waste things.
Yeah.
You know, so I throw things out and I feel bad. Mm-hmm. So that's, for me, that's reason enough. You know, but if you're going to spend a lot of public money and say require, you know, New York State has passed a law that says if there's a place for us to recycle our food waste, to compost it or put it through an anaerobic digester, within 25 miles of us, we're going to have to recycle our food waste in 2022. And that's going to cost a lot of money, and it may cost a lot of energy, and depending on how much weight you want to put on trucks driving around and this sort of thing, it may cause more pollution than it prevents. So you want to do that? Well, a life cycle analysis is intended to say, yes, you do want to do this because it'll make the environment better. You know, you get funny results. So the warm results all had positive results. So what that said is we could solve this global warming problem if we just landfilled enough stuff. You like that, right? You know, that's
capture the carbon in the landfill.
Capture the carbon in the landfill, yes.
I think we are nearing.
Yes, one last question.
Last question? Cool. So you mentioned before that there's a certain waste hierarchy that municipalities should follow when disposing of the garbage. My question is, so does 120 AA have, like, is that a pretty big factor in municipalities deciding on how to follow the hierarchy?
No.
Like if there's a material that has more value than another, do they just go straight to the landfill, or do they choose something else in the hierarchy based on what they can get from it?
Most places do what they have been doing for a long time, and they think it works, and they think that they've incorporated in the easy, basic recycling steps, and people are having a hard time following that. They don't want to make it too much more complicated. But the notion, very few managers want to change things if they don't have to, especially if things seem to be running well and there's public acceptance. So until Brookhaven said we're not going to recycle glass anymore, nobody cared about the Brookhaven recycling program. It was just a thing that was. And the town would change from dual stream to single stream, and people would say, oh, this is terrible. And then they'd say, oh, no, this is great. This is easier. And then the town would say, well, we're switching back. And they'd say, no, 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 you can't do that. Don't change things. We're happy, you know. Well, but it's not as good. It doesn't matter. This is easier. So it's those kinds of decisions are hard. New York State would like it, yes, that if you had to financially evaluate each and every material and then had to require the ones that made economic sense for you, they would like to see people do that sort of decision making. Okay? Imagine that.
Okay. David, thank you very much.
Thank you.